Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Joe Polchinski, who's come up to us from UC Santa Barbara, where he works at the Kavli Institute for Theoretical Physics as a permanent member there. Joe did his BS at Caltech and then PhD at UC Berkeley under Stanley Mandelstam, and then did postdocs at SLAC here in the South Bay and at Harvard. And then he moved to UT Austin, where he was a professor for a while. And then 1992 he moved to UC Santa Barbara, where he's currently in residence there. In 1998 he published a 2-volume textbook entitled String Theory. In 2008 he was a recipient of the Dirac Medal for his work on superstrings. He's well known in the theoretical physics community for his work on D-branes, which are extended objects on which strings can end with Dirichlet boundary conditions, and he linked these D-branes to black P-branes of supergravity, which then has led to such concepts as the holographic principle and M-theory duality. Last year in July, Joe published a paper about radiation from black holes that showed that relativity theory equivalence principle may be incorrect. So we're going to hear a whole lot more about that during his talk. So please join me in welcoming Joe.
Is that working? Okay, okay, very good. So yeah, the big problem that underlies what I'm talking about is the need to find a theory that incorporates both quantum mechanics and Einstein's theory of general relativity. And this is a very theoretical subject. It's much more theoretical than the typical talk in this series. And so I want to start by saying a little bit about how this works, how one can make progress in this way. And in fact, a center of this subject is various thought experiments involving quantum mechanics and black holes. And so I wanted to start by talking, to set this up, about an earlier thought experiment, one of my favorite thought experiments, because it's rather parallel to what we're trying to do. And this is the thought experiment that Maxwell used in the 1860s to complete the theory of electromagnetism. So here are Maxwell's equations, a common T-shirt design. How many of you own a T-shirt like this? Anyway. But before Maxwell came along, the T-shirt looked like that. There was a term missing. And these equations, as they stand, had really been discovered, well, theory played a role, but they were really discovered by direct experiment. So Gauss's law, which says that electric charges produce electric fields. Ampere's law, which says electric currents produce magnetic fields. Faraday's law, magnetic fields can also produce electric fields if they're changing in time. And these equations, as they stand, were a complete account, a very good account of all of the experimental data about the behavior of electric and magnetic fields. But they couldn't be complete. There's a problem with these equations, and it was exposed. One way to expose it was by a thought experiment, a simple thought experiment. Here's a circuit with just two elements. It just has a capacitor, stores charge, and an alternating current. And the question that the measurement that one needs to make is the magnetic field near the capacitor, near where that X is. And the problem is that those equations that I showed you don't give a consistent answer for what you would get. There are different ways to apply them. You can integrate sort of across the wire or between the plates. And depending on how you apply those equations, you get different predictions. So there's something wrong. They're not a complete set of equations. And guided by this contradiction and guided by mechanical models that he tried to build, he was led to realize that one more term was needed. And so there are the equations as they came to him, and there's his term. And of course, the bonus he got, besides having finally a complete set of equations for electromagnetism, is the discovery of the nature of light, the discovery that light is simply electric and magnetic fields. With his term, you can have a propagating wave made out of these fields. So here's a previous success of theory, and what are the morals? So the first is, why was this a thought experiment and not a real experiment? Why didn't somebody just build this little circuit and measure the field? And it's because it required, to get a large enough effect, it required gigahertz frequencies, and in the 1800s, it wasn't clear how to achieve that. Hertz figured it out, but it took him 25 years. And so that's why it wasn't a real experiment. And the second question is, why did this work? How can one make progress in this way by pure thought? And of course, it wasn't really pure thought. The experimentalists had done most of the work. They had found the rest of the equations, and it was just this one term that's missing. And so in some sense, theory is very effective when you already know a lot, and you're trying to fit it together into a more complete theory. OK, so in quantum gravity now, the subject that I'm pursuing, we're in a very similar situation. First of all, there's a natural time scale associated with quantum gravity. If you take the three most important constants of nature, Planck's constant, Newton's constant, the gravitational constant, and the speed of light, there's a unique way to combine them to get a time scale. That's the Planck time, and you see it's extraordinarily short. It's around 10 to the minus 44 seconds. So it's, roughly speaking, a giga to the fifth. You need to reach the level of a giga to the fifth hertz to see quantum gravitational effects. And this time scale is far beyond the reach of current experiments, just as the gigahertz scale, even more so than the gigahertz scale was in Maxwell's time. So that's why theory is so important here. And secondly, the other side is we already know a lot. We have a theory of gravity. We have Einstein's theory, which is extraordinarily successful, been tested many times. We have quantum mechanics describing the atomic world and below. Again, extraordinarily successful, tested many times in many ways. So we know a lot. And the problem then is to fit these two theories together. And that's now where theory can come in. As with Maxwell, we can look at situations, maybe situations that we can't yet realize in practice, and ask, do these theories fit together, or is there something that we're missing, as Maxwell found? So I'd like to pursue this. So this little calculation here that gives this time. So I'd like to say a few more words about that. So this calculation was first done by Max Planck in 1899, really very early. So this was the year that he discovered the black body radiation law, the year that he first realized there was this new constant of nature, h bar. And one of the very first things he did with it was to say, OK, hey, this constant is as important as the speed of light and Newton's constant. And so let's see what they tell us about basically the basic scales of nature. And he identified this very short time scale and also this very short distance scale. And it's the fact that these times and distances are so short that makes quantum gravity so hard. So I went back to his original papers to see if he'd ever commented about on the very small nature of these things and what that would mean. And I don't see that he ever did, but he said something very interesting, and it's especially interesting for this audience. Here's what he said. He said, these units necessarily retain their meaning for all times and for all civilizations, even extraterrestrial and non-human ones, and can therefore be designated as natural units. I guess people are always the same. It seemed like a funny thing to be thinking about in 1899. But his point was simply that, that these numbers are so important that any intelligent civilization anywhere that would identify them as the most important constant of nature, and therefore identify this time scale and this length scale as the basic units with respect to everything else should be measured. With respect to everything else should be measured. Now, when he said this, and actually for the next 80 years, this was either forgotten or even regarded as silly. But now his insight really has come to the front as we try to move forward. So it's interesting that Planck picked on, say, these three numbers, and not some other number like the electron mass, because in fact, each of these three constants of nature would be, in the next 25 years, the focus of a revolution in physics. So the speed of light, of course, is the key parameter in special relativity. Newton's constant is the key constant in general relativity. And finally, h, or h bar, I guess I left the bar off this one, is the key constant that governs where quantum behavior sets in. And so these three revolutions all around 100 years ago changed the way we think about space and time and matter and even reality. And they still today remain the center of our understandings of those things. But having these three new principles still raises new problems, because it's one thing to understand these three principles separately and on their own. But when you consider two or more of them acting at the same time, then again, there's the potential for conflict. There's the potential for some new ingredients to be needed to fit them together. And again, my main point is fitting together the last two, quantum mechanics and general relativity. But I want to just briefly mention the earlier enterprise of making quantum mechanics and special relativity work together. So this is Schrödinger's equation up on the top here. So the equation that Schrödinger had found that governed, to very good approximation, the quantum behavior of atoms and molecules, their energy levels, and wave functions, and so on. This equation was successful experimentally, but it fails for particles that are moving close to the speed of light. It incorporates the quantum principle. It doesn't incorporate general relativity. And so Dirac, playing with this, solved this. He found an equation. Which agrees with Schrödinger's equation for things that are moving not too fast. They have, if you take this and make the velocity small, you actually get this. But it does correctly incorporate the relativity principle. So he succeeded in combining the two, and he got an unexpected bonus. It didn't seem like a bonus at first, because it seemed like a problem, which is that this equation did what it was supposed to do, but it has twice as many solutions as were expected. It sort of had solutions that agree with Schrödinger's, then it had another whole set of them that were unexpected. And it took a little time for Dirac to realize that what this meant was he was predicting the existence of a new particle. He was predicting the existence of antimatter. And this was discovered 2 years after the prediction by Anderson, by Carl Anderson, this photographic plate. There's this hair-thin track here of a particle moving in an electric field. And from the curvature of the field, one knows that it's a positively charged electron. So in both Maxwell's and Dirac's discoveries, it's interesting to note that when you unify things, when you figure out how things fit together, you get unexpected bonuses. Maxwell fit electricity and magnetism together and suddenly understood the nature of light. Dirac fit quantum mechanics and special relativity together and unexpectedly predicted antimatter. Now, before I go on to general relativity, I want to mention one more thing, because the story of special relativity and quantum mechanics didn't end with Dirac. In fact, you may know that just this morning, the Nobel Prize was awarded to Peter Higgs and Francois Englert for predicting the Higgs boson, which was discovered at CERN last year. And this discovery really was the completion of the standard model. It was the completion of our understanding of the building blocks of ordinary matter. And this theory, so Higgs's work and Englert's work was actually 50 years ago. And this standard model, this very successful model of ordinary matter, took form in 1971. And it's interesting that, well, depending on when you count from, the theory predicted at least 5 new particles. And one by one, they've been discovered. The Higgs is actually the last of them. And they've been discovered with the precise properties that the theory predicted. So this is a great triumph. And again, I'm a theorist and I'm focusing on a theoretical subject. And this is an area where theory got ahead of experiment for a while. Peter Higgs was 50 years ahead of the LHC, ahead of the experimental discovery. And the question again is, how can theory be so effective? How could one make such precise predictions, such certain predictions? And again, it has a lot. There were more ingredients than with Dirac. It required new ideas, new kinds of experiments. But again, the fact that the theory has to correctly incorporate both the relativity principle and quantum mechanics very strongly constrains it. And it's the reason why the model makes such precise predictions. So this brings us to now the main subject, which is trying to do the same thing now for quantum mechanics plus general relativity. So general relativity is very successful on the cosmic scale, describing, well, I guess one of its first great successes is describing tight neutron binaries where the curvature of space is very large, describing the expansion of the universe, describing very precise corrections to Newton's law in our own solar system. And quantum mechanics is very successful on the atomic scale. I recently heard the assertion that a third of our gross national product basically is based on quantum mechanics. The entire electronics industry is based on quantum mechanics. I'm surprised it's just a third. But it's important and it's hugely successful in explaining microscopic physics. And now, again, we would like to confront these. We'd like to look at situations where both of these principles are important at the same time. The curvature of space and time that comes with general relativity and this quantum uncertainty principle that comes with quantum mechanics. But because of Planck's calculation, what this means is that environments where both quantum effects and general relativistic effects are important at the same time are going to be very extreme, and it's hard to find any in nature. But of course, we can imagine them. We can think about situations that could arise in principle and ask, what do we learn from this? And so I'll mention three environments where both would operate at the same time. So one of them is in particle physics at extremely high energy. So I mentioned that the time scale for quantum gravity is a giga to the 5 gigahertz. The LHC more or less reaches the level of a gigahertz. So it's far beyond Hertz himself, who got 1 giga, but still well short of what you would need to probe quantum gravity. Nevertheless, you can imagine the situation of having enough energy, and again ask, do the theories make consistent predictions or not? The second place is the very early universe. The universe is expanding. And it was once much smaller than it is today, small enough that, again, quantum mechanics and gravity were working at the same time. And finally, and my main subject, is the cores and even the horizons of black holes. But I'll first say a few words about the first two. You imagine smacking together a couple of particles with enough energy. There's a Planck energy too that again, quantum gravitational effects be important. And if you take the existing theories, you do get a contradiction. You do get nonsense because in fact you get infinite answers for the rate of scattering. And this kind of problem has come up before. It's always an important clue as to the correct theory. This one is especially difficult. But the idea that was hit on that seems to solve it is to imagine that the basic building blocks of nature, instead of being little particles like those dots there, are actually large. They're actually expanded out into loops of string. And that's a strange idea. It's not something that immediately seemed like the right idea. There was a period of about 10 years when there were only about 3 people in the world working on it. But eventually enough positive results piled up and enough failures piled up in other areas that this caught wide attention, and today it remains the central idea for how things work. Now Adrian mentioned that I wrote a textbook on this subject. Actually, you will not hear a lot about strings themselves in this talk, but they do lie beneath some of the things that I'll tell you about. And then the second environment is the early moments of the Big Bang. And actually, so we already have strong evidence that quantum mechanics was important in the early universe. So we now have these precise measurements of the pattern of the cosmic microwave background radiation, here presented both as a plot, both as a graph and just a picture. And also measurements of the distributions of galaxies and so on. And there's very strong evidence from the fit between theory and experiment that all the structure in the universe, the pattern of the galaxies and therefore the origin of the galaxies and therefore of all the structures within them like stars and planets and us, come back to quantum fluctuations in the very early universe that were amplified by gravity as the universe expanded. Now, here's part of nature, of real nature, the center of nature in some sense, that does involve both quantum mechanics and general relativity of the expanding universe. But in fact, these fluctuations originated not at the Planck time, but slightly after. They don't really reach back to the part of the theory that we don't understand yet. But if we want, there are at least a dozen different theories of what happened at the Planck time. Different kinds of inflation, tunnelings, universes collapsing and re-expanding. And if we really want to understand what happened at the beginning, we are going to need a theory that correctly incorporates both quantum mechanics and gravity. In fact, this is, if you ask why are you pursuing this, there's two answers. One is, this is clearly the key problem, but also, as with the other examples I mentioned, there's also the unexpected, that when we fit these things together, we will learn something that we didn't expect that we will learn. Okay, black holes, finally. So for the purpose of this talk, this is what a black hole looks like. So this is kind of schematic, but what it's illustrating is a space that is very highly curved. So this is the final fate of massive objects. They reach a point where they can't resist the force of gravity. Nothing can resist it past a certain point. And they collapse. And as far as Einstein's theory can say, they collapse down to a point of zero size, a point of infinite density and infinite curvature. Now, we all expect that when we understand things better, that point will be resolved into something fuzzier and not quite so infinite. But that's not the main story here, because there's another interesting place in the black hole, which is the horizon, the point of no return. So this is simply the place where the potential becomes so steep that you can't escape. Anything that passes that dashed line is doomed to fall into the singularity. Even light can't escape from behind the horizon. Now, the horizon itself, there's nothing special there. I should erase the dashed line because because in fact, can I do that in real time? Because in fact, what Einstein's equations say is that space here is perfectly smooth. An infalling, an astronaut in free fall would pass through the horizon without seeing anything unusual. They would simply not be able to summon enough energy or anything to escape again. Okay, so that's what a black hole will look like. And so in the early 70s, Bekenstein and Hawking especially, and others, well, after understanding black holes, after thinking about their astrophysical significance, which of course has grown, they also began to think about what would happen if you try to apply quantum mechanics to the behavior of a black hole. And they uncovered a puzzle and a paradox, but two interlinked puzzles. So the entropy puzzle is this. General relativity describes the black hole as a smooth featureless geometry. Well, there's the feature at the bottom, but the singularity. But for the most part, it's a featureless geometry. In particular, In particular, it doesn't matter what kind of star you threw in. It doesn't matter what you threw in with the star. Once the star has collapsed into that singularity, the geometry doesn't depend at all on what you threw in. One says black holes have no hair. So general relativity says that black holes are these featureless geometries. Quantum mechanics, though, strongly suggests that black holes have some kind of atomic or bit substructure. And there's two kinds of evidence for that. One of them is an information, well, I'm about to tell you, one due to Bekenstein, one due to Hawking. And there's a further lesson which I'll get to, which is something called the holographic principle, which Adrian mentioned. So what Bekenstein did was to calculate the information storage capacity of a black hole. So he's imagining throwing information, bits of information into a black hole. And there's a minimum energy to add a bit to the black hole, because the black hole has a size. So in these equations, don't really pay attention to h bars, g's, and c's, the constants of nature. Pay attention to the r's, which are the size of the black hole. So there's a certain minimum energy to add a bit to a black hole, because you have to fit whatever particle it is into the black hole. It has some finite size, and therefore the uncertainty principle says it has some non-zero energy. And so here's the minimum energy to add one bit. And then Einstein's theory tells us for a black hole of given radius, what is its total energy? It's here, and it's linear in r. It has 1 power of r, and then the constant of nature to get the units right. And so if you divide the total energy by the energy per bit, you get an estimate of the number of bits in the black hole, and here it is. And I'll say more about the significance of this formula in a second. Hawking did a slightly different thing. Hawking, actually, by the way, this is all sort of rough. Hawking's calculation actually gets the 4s and the pi's in the formula correctly, but I'm not bothering to write those. Hawking found, and I'll say more about this shortly, that black holes are not actually black, that due to quantum effects, they radiate, they have a temperature. And when systems have a temperature, then there's a basic unit of energy, kT. And in systems that have a temperature, well, you think about it, temperature usually means there's something like atoms that are in motion. And in particular, one can sort of count the number of atoms by taking the total energy of the system, total thermal energy, and divide it by this thermal unit kT. And Hawking comes to the same number of bits that Bekenstein did. So what are these bits? You don't see them in general relativity. You see this smooth space. OK, before I will tell you more about these bits as we go on. But I want to point out something interesting about this particular formula. So again, the thing to pay attention to is, again, the powers of the radius, the size of the system. So this is the information storage capacity of a black hole. And for most systems, their information storage capacity goes as their volume. Because if you have a box, whatever you're storing your information on, the number of those you can put in the box goes as the volume of the box, the cube of the cube of its size, of its linear size. But for black holes, the information storage capacity goes as the square. It goes as the surface area of the box rather than the volume. And so it suggests a picture both of the black hole and really of general systems in quantum gravity, where the basic degrees of freedom live on the surface of the object. They're some kind of dense bits on the surface of the object rather than living inside of it. So this is called the holographic principle by analogy to holograms, which store an image of a three-dimensional picture in a two-dimensional plate. This is one clue from thinking about, again, black holes and information, that there's something very different about quantum gravity from any other theory, any other system we've studied before. It's holographic. The basic bits, the basic storage of information don't kind of live at points in the space itself. They live on the surface of the space. So that's the entry puzzle. That's the information storage capacity of black holes. That's kind of the lesson from that part of the thought experiment. Now the information paradox. So as I said, Hawking's great discovery, one of his great discoveries, is that black holes aren't black. They slowly lose their energy due to a quantum process. So quantum mechanics says that empty space is full of antiparticle-particle pairs that are always popping into and out of existence. And once they appear, they can't stick around for long because they don't have enough energy to, and so the uncertainty principle says they can only hang around for a little while. But in the presence of a black hole, something interesting can happen. If one of these pairs pops into existence right near the horizon, then what can happen is one of the pair can be sucked into the singularity, and then the other one can escape. And so what happens is that near the horizon, essentially the gravitational field allows them to separate. It does work on the particles, and so you can produce a real particle that escapes from the black hole and carries energy away. And this is, again, this uses both quantum mechanics and general relativity, but it uses it in a way that seems not to lead to contradictions, not directly. And the conclusion is that as this process repeats many, many times, the black hole eventually loses all of its energy in this way, and you're left then with just flat space with photons streaming out. Now, this is a very weak process. So again, this is a thought experiment. For the black holes in our universe, this process would have, had very little effect as yet. In fact, it would be completely negligible. But again, we're using thought experiments for reasons that I explained at the beginning of my talk. A black hole in sufficient isolation and given sufficient time will decay into photons. Yes, please.
What sort of time to evaporate?
So let me answer the question period, because I don't have. I'll do the calculation kind of in real time here. Yeah. No, it's okay. It's let me think. Yeah. I'll actually. Well, when Hawking first actually hit on this phenomenon. So now we know of black holes that come in kind of two different sizes: star mass black holes from collapse of old stars, and black holes in the cores of galaxies with masses of 1 million to 1 billion stars. When Hawking hit on this, there was still a possibility that in the early universe, in the course of the Big Bang, much smaller black holes would have formed. And so there is some number, whether it's 1 gram or 100 grams. There's probably somewhat larger than that still. No, but there is some small enough mass of black hole which, had it formed in the early universe, would be kind of finishing its evaporation today. But for the stellar mass black holes, it's far longer than the age of the universe. Okay, but now. After discovering the information paradox, after discovering this evaporation, Hawking realized a couple years later that it leads to a paradox, because you can imagine throwing information into a black hole, and I don't know if you can tell, but this is a copy of Hawking's book. And once it crosses the horizon, then nothing behind the horizon can send signals out. We can no longer read the book or have any clue as to what it is. And once the black hole finishes evaporating, the outgoing photons, the outgoing quanta, have no memory. They don't reflect in any way what was thrown in. And that's what Hawking's calculation shows. So it doesn't matter whether you threw in Hawking's book or my book, the photons would look exactly the same. Or if you threw in rocks, they would look exactly the same. Now, the laws of quantum mechanics don't allow information to be destroyed in this way. It can be scrambled up a lot, but it can always be reproduced in principle. So I wrote down Schrödinger's equation, and basically, today we're just dealing with bigger and bigger versions of Schrödinger's equation, and they all have this property that they don't destroy information. And in fact, equations that destroy information are very ugly. They're not very appealing as fundamental theories. But Hawking argued that black holes do destroy information, and therefore quantum mechanics has to be modified. If you want to keep quantum mechanics, then somehow somehow the information that falls behind the horizon has to escape, which means light can't escape, so somehow the information has to travel faster than light. And so this was a very sharp confrontation, a very sharp conflict between what quantum mechanics predicts in every system that it applies to and what relativity tells us about the geometry of a black hole. And Hawking had a very picturesque way to summarize this. God not only plays dice, he sometimes throws the dice where they cannot be seen. So God playing dice was Einstein's way of describing quantum mechanics and why he didn't like quantum mechanics. And now Hawking is saying it's even worse. Because in addition to the basic uncertainty of quantum mechanics, there's the additional uncertainty of not even knowing sort of what the wave function is. Now I'm really in awe of Hawking and his original paper on this subject, well, the many things he's done, but this one in particular, because this was a challenge, telling physicists that quantum mechanics broke down. And for 40 years, people tried to find the mistake in Hawking's paper. And there are a lot of subtleties, obviously, in this subject, and they were raised, and they failed. Hawking had really seen very clearly at the beginning that this was a very sharp paradox, that something has to give. And he thought it's quantum mechanics that gives, but something has to give in a big way. OK, so again, so Hawking produced this, and again, for a long time, people tried to find his mistake or to argue that quantum mechanics can be modified. And there was no appealing picture. I know there were people who very strongly believed either in quantum mechanics or in relativity. I couldn't see an appealing resolution of this. Everything seemed unsatisfactory. And it's interesting that we think, many of us who certainly were on the fence before, now believe that we know which fails. We know what happened. We know at least whether the information gets out of the black hole. And it's because of a discovery by this fellow, Juan Maldacena. So many quantum systems have been found to have a property known as duality. And actually, the first duality is wave-particle duality, where waves and particles are actually the same thing, seen in different regimes. But this turns out to be a very common property in quantum systems, where you have some system, and you imagine first that h bar is small and is not very quantum, it's kind of classical. And as you make h bar bigger, then the quantum effects get bigger, meaning that the uncertainties get bigger, things are fluctuating more and more. If you were talking about quantum gravity, space-time would be fluctuating more and more. But when h bar gets very, very big, and these quantum fluctuations are completely out of control, and you have no picture of what's happening, in many systems there is some new simple description, some new classical description that emerges that describes kind of a different set of variables. And it often is very different from the ones that you started with. So it's two different systems, or two systems that look very, very different, but are secretly the same. It's just that one is very quantum and one is very classical, and when one is very quantum, one is very classical. And so Maldacena found an example of this, a duality between a quantum mechanical black hole, the thing that we're trying to understand, and a much more ordinary system, which is an ordinary gas of strongly interacting particles, very similar to the quarks and gluons of the strong nuclear force. So here's the duality. And he discovered this, well, first of all, by puzzling over the black hole information paradox, but also by bringing in some ingredients from string theory, strings and branes. And it's interesting because I don't have any strings and branes in the picture. They actually form sort of the bridge between the two sides. So again, this is the black hole I've been talking about. And this is a bunch, again, of these strongly interacting particles like we have in the strong nuclear force, which have been heated up to form some kind of gas or plasma. And these two very different, what he found by comparing calculations on the two sides is that these two very different looking systems are actually the same. When this one is very quantum, then this one is very classical, and vice versa. So this is like Maxwell. It's an unexpected connection between widely different areas of physics. This is quantum gravity, this great puzzle. And this is something like the strong nuclear force, which we understand very, very well. It's not exactly the same as the strong nuclear force, but it's the same kind of theory. And so like Maxwell, this is a completely unexpected connection between widely different parts of physics. It is the most cited paper in the history of theoretical physics with 9,000 citations. And it's significant in many ways, but it is significant for us because it's the most complete construction of quantum gravity to date. And it teaches a number of lessons. First of all, because quarks and gluons, because the strong nuclear force obeys ordinary quantum mechanics, it must be that quantum black holes do as well. There must be something wrong with Hawking's argument. Second, it provides exactly the bits in number that were predicted by Bekenstein-Hawking. So you're seeing here basically the bits of the black hole. And the third thing is that it in fact is holographic, that under the dictionary between these two quantum systems, the bits actually live on the surface surrounding the black hole. So Maldaceni's duality very nicely dovetailed with these thought experiments of Bekenstein and Hawking. And in 2004, Hawking very publicly changed his mind and paid off a bet that he had made. But I have to say that I was surprised that he gave up. I think he gave up because he was convinced by the evidence from Maldaceni's theory. He was convinced that this is a true thing and that the conclusion has to be true. But what was not satisfying was we still didn't know what was wrong with his original argument. So the lesson here for now is that Maldaceni's discovery, well, it moved the field forward greatly, and it seemed to answer many questions, but it didn't answer every question. Again, the obvious question it didn't answer is where exactly did Hawking go wrong? How does the information get out? Does it really travel faster than light? But also this holographic principle, which Hawking and Bekenstein had sort of laid the groundwork for, and Susskind and then Maldacena had sort of confirmed, is very different from anything we've encountered in physics before. How does it really work in detail? Maldacena's duality works in a very special space known as anti-de Sitter space. It's a special kind of box that you can put gravity inside. And so this is sometimes known as ADS-CFT duality. But how does this holographic principle work in a universe like ours, which isn't in a box, but is in an expanding space-time? This is a crucial question. And a bridge maybe to this is to think about the insides of black holes. Because the inside of a black hole is a lot like a Big Bang. It's kind of like a Big Bang in reverse. In the Big Bang, the universe started very dense and expanded. Inside a black hole, the universe is collapsing to a singularity. So it involves many of the same questions, but in reverse. So this brings me almost up to the present and to the firewall, and I have just about the right amount of time. And so I'll describe. So these after Hawking's concession, after Maldacena's discovery, many things were answered, but there was a sense that there were these things we didn't know. And actually, so many of you may know this fellow. He's Lenny Susskind, a local character, actually a very brilliant physicist and a very, very good speaker. So he actually laid out a framework for sort of how the whole thing works. And it's, first of all, information is not lost. This is now taken as agreed. But he also argued that it really wasn't necessary that anything too radical happened to get the information out. So an observer who stays outside the black hole sees nothing unusual. And an observer who falls into the black hole sees nothing unusual. But taken together, they see something which seems contradictory. So the question is, how does the information get out of the black hole? Well, then he says it doesn't actually get out of the black hole. You have a new relativity principle where one observer, the one who falls in, sees the information inside, and one observer who stays outside sees the same information outside. And this seemed actually to fit very nicely with with Maldaceno's discovery. And so I've been trying over some time to make a model of how this would work. And I've failed many times to make a model that has all of these properties. And ultimately, with my students and my brilliant young collaborator Don Marolf a year ago, we realized that we were failing because you can't do it. Because these postulates are not consistent with each other. They imply an impossible quantum state for the Hawking radiation. So it's a short argument. It fits kind of on one slide. So the top picture again is my picture of Hawking evaporation. There's a process, a quantum process, that produces these particles. It produces a pair. But it's a quantum process. It produces a superposition. That is, either there is a pair, one particle inside and one particle outside, or there's no pair, 0 and 0. And in quantum mechanics, this is what's known as an entangled state, where you have two systems, two particles, say, and the state of one of them depends on the state of the other. And this is actually, entanglement is something which is playing a larger and larger role as people go on to try to build quantum computers and in exotic phases of condensed matter, and now in trying to understand quantum mechanics and gravity. Now, conservation of information. So I gave you sort of basically what we did is we took Hawking's original argument for the information paradox and ran it backwards. We said if information is not lost, what breaks down? And what conservation of information requires that all the outgoing Hawking photons be entangled with each other. And so we have this problem, because quantum mechanics does no allows. It does not allow a single particle to be both entangled with. Entanglement is monogamous. A single particle cannot be strongly entangled with two other particles. And I've written down here, if this means anything to you, some quantum states which are not the same. This is the state that Hawking's calculation predicts, in which you go. So I've simplified the system to three particles. The first one is inside the black hole. The second one is its partner coming out. And the third one is some earlier Hawking photon. And Hawking's calculation says that the first two have to be entangled. But if you want to get the information out, then the second and third have to be entangled. And they can't all be entangled. It's one or the other. And so if you insist that information is not lost, then you lose this entanglement between this pair that you produced. And what does that imply? Well, that's bad, because breaking the entanglement is sort of like breaking a chemical bond. It's not exactly the same, but it's a pretty good analogy. So in some sense, to get the information out, it's sort of like we have to break a chemical bond that stretches across the horizon. And as with breaking a chemical bond, this implies that there is some excitation, that there is some energy there. And so if information is not lost, if we run this backwards, then in fact, there is an enormous energy. There is a wall of high energy particles, which a firewall is probably not a good name. I don't take credit for the name. That was one of my collaborators, but has come to be called a firewall. So instead of what Einstein's theory predicts, that the infalling observer in free fall sees a smooth space-time, instead the infalling observer, out of the blue, in a region where nothing should be happening, instead encounters seemingly, well, at the very least, a lot of energy and very possibly the end of space itself, as though the singularity, instead of sitting way down here at the bottom, has migrated out to the horizon. So once again, this is a sharp conflict between quantum mechanics and space-time, even sharper than before, because quantum mechanics requires space-time to cease to exist for no apparent reason. And it's not clear where this is going. So the history of this subject has again been a conflict between quantum mechanics and space-time. Hawking was ready to give up quantum mechanics. Maldacena saved it. But now quantum mechanics is really going too far. It's really doing something very radical to space-time if this is true. So we hit on this argument a year ago. We tried to kill it. It may sound simple. I mean, it fits on one slide or 1.5 slides. And it really is simple. It's so simple that we were surprised no one had ever said this before. But we couldn't kill it. We talked to other people. No one else could kill it. Eventually, I called the Godfather, Lenny, expecting that he would tell me, oh, he thought about this 10 years ago, and it's all fine, and it's all written down somewhere. But no, he was quickly as confused as we are. And so after a year and over 100 papers, no one knows what's going on. No one has found any simple mistake in our reasoning. No one, including me, really believes deeply that this can happen. Maybe it does. I mean, we have right now there's no dynamical mechanism that would account for how this appears. But this holographic principle is pretty strange. There may be a reason why space-time ends at the horizon. Most thinking is that there has to be some subtle assumption that breaks down. And what's interesting is that as you look at the papers, most of them are starting to relax the rules of quantum mechanics, just subtly. But in this battle between quantum and space-time, maybe quantum mechanics is giving a little. And there's this slogan you may hear about more in the future: space-time emerging from entanglement in quantum systems. So to conclude, some things you might matter. Are there any observational effects for black holes? And it's way too early to say. Some of the ideas being discussed would lead to fairly dramatic effects when black holes collide. But many of the ideas would only affect the behavior behind the horizon. Are there any consequences for cosmology? Now, I've been talking about the black hole horizon, but in cosmology there are horizons too. There are distant galaxies all the time, which are passing forever out of our view due to the expansion of the universe. So we're continually crossing horizons and not burning up. But there may be subtle effects that we haven't thought to look for. Again, it's too early to say. So before I conclude, for this audience, there's one speculation that comes up. This is totally orthogonal to anything I've just said. And, well, not anyway. I mentioned that black holes have these bits. The number of bits in a large black hole is larger than the number of atoms in the entire visible universe. So that black hole has an information storage capacity greater than if you took all the atoms in the entire universe and put them together. And so it's natural to ask, could these bits, could this quantum system, could it support life? Certainly life to exist and to evolve, the first thing it needs is some large number of small building blocks that can rearrange in many ways and try to form stable structures. That would be cool. But based on our current best understanding, the bits in black holes, life requires, in addition to large numbers of building blocks, it requires that they can form stable structures, like atoms and nuclei and larger structures. Our best understanding of the bits inside black holes is that they can't form stable structures. They come to thermal equilibrium very quickly and very efficiently. But it's clear, this whole discussion is teaching us that some of our thinking about black holes was simple-minded. And so I throw this out there as something which is fun to think about. But again, there's reason to think that these large number of bits aren't very useful because they quickly reach a state of maximum entropy. Anyway, to conclude, already in the past, thought experiments with black holes have led to surprising and important discoveries, the bits, the holographic principle, multisinus duality. And now we have a puzzle which seems as frustrating and challenging as anything in the past in this subject. And the hope is that will lead us to an even deeper understanding of quantum gravity. Thank you.
Joe, if I could start with the first question. I know there'll be a couple that we'll get to in just a sec. In the past, there's been talk about travel through wormhole type of horizons. How does this play in with firewalls?
This is extremely interesting because It's been known for a long time that you can. So there are black holes that form and collapse. But if you take Einstein's equations, there are also solutions which, as you say, have two black holes connected through their center by a wormhole. And the interesting thing is that you can fall into the black hole and receive sort of messages from either side, but the wormhole collapses too quickly for you to actually send a message from one side to the other. And this is very similar to something which superficially is very different, the EPR experiment, the Einstein-Podolsky-Rosen experiment in quantum mechanics, where if you have two entangled particles, you can't actually use, superficially, this bothered Einstein, manipulating one particle changes the state of the other. But in fact, it's clear that you cannot use this to send information faster than light. So both the black hole with its wormhole and the EPR system are systems which are naively connected, but where there's no actual ability to send a message. And the latest thinking in the subject, and this is something I alluded to that goes back to Maldacena and Susskind, is that in fact the analogy between the bridge and the EPR experiment is no accident, but in some sense is a key to understanding where space-time comes from.
Yeah, so you framed the argument in terms of this entanglement.
Yes.
And that, you know, it leads to some difficulty of an understanding because you're thinking of non-localities and things like that. Can you frame the entire argument just in terms of a vacuum state and somebody falling into a black hole without any use of entanglement? Do you really need the entanglement to make this argument?
I believe the answer is yes. That is, actually entanglement, well, I believe the answer is yes, because at the bottom, this is a conflict between quantum mechanics and general relativity. In some sense, the thing that makes quantum mechanics so special is this notion of entanglement. It's the thing. It's the thing that quantum mechanics has that that isn't there in classical. It's therefore something which, of course, is very hard to explain, hard to draw. But I think the entanglement is essential to the paradox. If we didn't have the entanglement, we wouldn't have quantum mechanics. Yeah.
I believe there was something published earlier this year with regard to space-time, a different view of the interior of the black hole, which doesn't require a model that doesn't require singularity. Is that something that would affect some of this?
I should say, I mean, there's been a lot. This idea has many predecessors, and now I'm not sure which specific one. Do you remember any names or anything that would help me know which? So,
but I think there was a funny part about it. I think they were only dealing with space-time and the significant curvature, but they hadn't addressed mass yet, which I didn't quite understand.
So the interesting thing is when you look at this picture, the singularity is obviously a troublesome place. And it wasn't obvious until Bekenstein and Hawking came along that even the horizon was already a troublesome place. And so it's not clear that anything that modifies the singularity, I mean, it seems, I mean, you know, anything that sort of smears out space-time even a little bit will modify the singularity. There are even ideas that when you fall into the singularity, you pass through a different, this is a different kind of wormhole from the one that I was responding to before. But there are ideas that when you pass through the singularity, you pass actually into a new baby universe. I don't know if this is related to, but those ideas, you know, what happens down here, there's already a problem out here. Fixing this doesn't fix it. Yeah. Of course, you know, again, I feel deeply that, you know, every logical argument I can make, every logical argument I've seen supports this conclusion, and I still don't believe it. I feel like there's some assumption that we're missing, which is yeah.
Somewhere recently I read that as you fall into a black hole, time slows down, and so that eventually when you get to the horizon, it actually stops. So is that true, and how does that relate to this?
So, well, time slows down is something you really can't say in relativity because different observers see different times. So what happens is you have an observer falling in. And again, the classical Einstein story is the observer falls in, and again, they don't know they're slowing down. Their clock runs at the rate, they're 1 second, 2 second, 3 second, 4 second, everything is fine. But if you think about that observer sending a series of pulses to someone at infinity, the closer they get to the horizon, the longer it takes that pulse to climb out. And once they reach the horizon, it takes infinite time. And so from someone who sits on the outside and looks at the clock of the inflowing observer, will see it moving more and more slowly. And again, this is it's a natural relativistic effect, and it doesn't at all conflict with, well, at least in classical general relativity, it doesn't at all conflict with the fact that a different observer sees his own clock moving along just fine. Now, maybe this problem is, maybe there is some connection between what you just said and this. Maybe in fact the horizon is a special place for some sort of global reason. We don't know.
Does any of this possibly relate to dark matter? And if life can't exist in a black hole, could it exist in dark matter?
Good. So I'm going to say no there, because all the sort of all the observational evidence is that dark matter is just some kind of particle that doesn't happen to interact with light. And of course, we know of other ones like neutrinos, but they're massless. And there's ample. I mean, it's not surprising that there are particles we haven't yet discovered. What's interesting is, and it's also not surprising that there are particles that don't interact with light. What's interesting is that some of them are what the evidence for dark matter says is that some of them are stable, and moreover that the early universe produced them to even more of those than it produced of ordinary matter. So no, I don't see a connection there.
So I was going to ask about dark matter, but since you just answered that question, I'm going to ask something about baby universes.
Yes.
And Hawking radiation,
Yes,
which is
yes.
to say, if you have a black hole that creates a baby universe and you wait long enough, does the baby universe get destroyed when the black hole bubbles away, or does it pop off and maintain its existence?
So good. So you can play with this. You can play with models which are not really physical, but where you tweak Einstein's equations to get rid of the singularity. And those models are consistent with the idea that that the baby universe basically that the universe kind of snaps and the baby universe hangs around after the black hole disappears. And so one thought is that baby universe sort of carries away the information that went into the black hole. Now, the problem with that is that it still leads to difficulties with formulating quantum mechanics in the universe that's left behind, and that always seemed troublesome. And now that we have again this duality of Maldacena, which not everyone believes, but which I think the evidence is overwhelming for, it seems to be inconsistent with the idea that baby universes carry information away.
If these firewalls are real, is there any chance to detect them, to observe them?
So of course, this would be fun. I would like the answer to that question to be yes. But nothing in the argument requires that, because what this loss of entanglement implies is sort of a sharp discontinuity between what you see outside and what you see inside. And so there's nothing that requires it. There are ideas out there for getting rid of the firewall. So I don't believe this, but my colleague Steve Giddings is trying to implement models which actually transport the information physically sort of faster than the speed of light. Those models would imply that when black holes collide, the space-time geometry is very different from what we expect. So there are ideas out there that would have observable effects. I'm pessimistic, unfortunately. Yeah. Oh, well, I'm pessimistic in the short run. In the long run, again, if I think that when we figure out what the right theory is, it will lead us to ask questions that we didn't think to ask, but I don't know what they are. Yes?
If you apply thought experiments to very, very large black holes,
Yes.
billions, where
Yes, yes.
you can conceive of going into it
Yes,
without
yes,
being
yes.
torn to spaghetti,
Yes.
do you still expect this?
So this is exactly right. This argument applies for black holes of all sizes. And again, black holes of any reasonable size live longer than the age of the universe, so it's something very idealized one's talking about. But the argument holds there, and I think you're disturbed by it, and you're right to be disturbed, because Einstein's equations say of space-time, well, as you say, as you fall down here, you're getting squeezed one way and stretched another, and you're getting spaghettified. But now, before you get spaghettified, you either burn up or go crunch or turn into some abstract bits of information.
The particles would not be created anywhere near, the infinitesimal rate.
Yes. That's right. Yeah, it's a very, 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 superficially, it's a very, very tiny effect. There's another thing, too, I should say, which is that this firewall, presumably, if it forms, doesn't form immediately. And there's no clear, there's different arguments for what the natural time scale would be. But it's one set of arguments would suggest, in fact, that for a large black hole, it forms very late, which would mean, in fact, that for astrophysical black holes, you would not have a problem. But we don't know yet. Yeah.
When they over here, when they talk about the size of black holes,
Yes.
they always relate it to the amount of ordinary matter that created them.
Yes.
Except, as you reminded us, most of the matter in the universe is dark matter.
Yes.
Do black holes not suck up dark matter?
No, they do. Oh, they certainly do. But gravity, everything, in fact, the reason that we know that dark matter exists is because it gravitates. We see it through its gravitational effect. And so they certainly do. And so every black hole that's out there has sucked up a certain amount of dark matter. They probably formed predominantly from ordinary matter, because dark matter has this annoying property that because it's so weakly interacting, it doesn't tend to clump. And so it doesn't tend to form into black holes or to fall into black holes. But in fact, this no hair statement means that regardless of what it formed from, whether it formed from ordinary matter or formed from dark matter, the final black hole looks the same.
Joe, we have one question from our online audience.
Yes.
If a black hole is subatomic space in matter filling in, how can her information reach inside the black hole unchanged beyond the event horizon?
Could you say that again?
If a black hole is subatomic space in matter filling in, how can information reach inside the black hole unchanged beyond the event horizon? It could be a
Having trouble
tricky
parsing
question to
that.
interpret.
I'm having trouble parsing the question, yeah.
Maybe
yeah.
we can, the beauty of having that online is we can answer it online as well. So other people who are thinking just that same question can check out our YouTube site where the answer can be posted. So if you have any more questions, I'd encourage you to come up and speak to Joe in person. And we have a special black hole mug. Well, at least it's black in color anyway. So has a couple of androids speaking the Drake equation to each other.
Very good. Thank you.
So please join me in thanking Joe for his great talk.